Talmon.
Thank you very much.
He will talk about the electron microscopy of extracellular vesicles.
Thank you very much. Very glad to be here. This is my first CLINAM. I'm a chemical engineer by, maybe we can have the first slide, please. I'm a chemical engineer by training and background and affiliation. So the way we come to this topic is through our interest in self-assembly or self-aggregation. And the tool that we use, the main tool that we use, is the electron microscope. And what I would like to do this morning is really to give you the very essence of how we can use electron microscopy to image extracellular vesicles and also to track how they are formed from the cell. And here it is. Thank you very much. So this is Haifa, where I come from. And I should give, first of all, tribute to the people who gave us money to play with what we play, the technical help from these two wonderful ladies, and 3 of the students that were involved in the data that I'm going to show you today. So basically, when we approach direct imaging by electron microscopy, we have to dwell on these 4 points. First of all is nanostructure preservation as we prepare the specimen for the electron microscope. And this is a main issue because when you use techniques like staining and drying, you definitely are on a dangerous course of changing your specimens. And the approach of doing it through cryo is, of course, giving us the much better chances of success. The other issue is the interaction between the electron beam and the specimen, and you have to use very low dose of electrons in order to get your image. You have to enhance image contrast, and staining is not an option, so you have to do it in an optical way. And finally, you have to work with an instrument that will give you sufficient resolution. So I'm going to emphasize these 3 points. So for cryo-TEM, and I'm going to skip all the technical details, you have to prepare your specimen in some kind of an enclosed chamber where you make sure the temperature is fixed and the concentration of your specimen is fixed. Because many of the systems, not necessarily extracellular vesicles, but the ones that we work with, are very sensitive to changes in temperature and in composition, and we have to make sure that we keep this in this kind of a chamber. Basically, what we do is we take an electron microscope grid covered with a perforated carbon film. We put a very small drop on it. We blot it from a very thin film, about 300 nanometers, and then we quench it into liquid ethane at its freezing point. This assures that the specimen is not frozen, but vitrified, which means that we avoid all the problems that are associated with the freezing process, and also with the electron optical artifacts that can come from a crystalline specimen. We take the vitrified specimen, we transfer it into a cold stage, and keeping it at a very low temperature, and we transfer it to the electron microscope. Now, this is the electron microscope that we use today. It doesn't look like you're given any old microscope. My students say that this looks more like an ATM machine. But when you open the doors, you can actually see inside that there is a very sophisticated 200 kV field emission gun electron microscope. These are pictures that were taken when it was installed at the Technion. The other issue, as I said, is how do you take the pictures with minimal dose, with minimum electrons? So to our help comes a very sophisticated electron camera. In this case, you can see the comparison. These are just a bundle of carbon nanotubes. On the left, you can see the picture taken with a modern, state-of-the-art, regular technology camera, and on the right, you see the same with the single electron counting camera, the direct imaging camera. And these images were taken at 2 electrons per angstrom squared. This is a very, very small dose. Typically, when you take a staining and drying picture, you take it at about 100,000 electrons per angstrom squared. So there's quite a change in this, and this is essential. because most of our specimens are very electron beam radiation sensitive, so you have to make sure that you use minimum electrons in order to record your images. The other thing, the other problem, as many of you know, is that most of our specimens have very low inherent contrast, which means that different domains in the specimen look the same. However, if you use a technique that is borrowed from light microscopy, and this is just a schematic of it, you are able to convert phase differences in the image to amplitude differences. And when you do that, you can make the invisible to the visible. Let me demonstrate this. What you see here is a very nice, clean, vitrified specimen of protein trimers. Can you see them? The answer is, the correct answer is no. What you see here is just a little fleck of ice. However, when I turn on the so-called phase plates, which convert phase changes into amplitude changes, you are able to see it very nicely. You see, this is the same fleck. Let me go back, invisible to the visible. So by combining all these things, you can actually really get very high resolution images of specimens that were prepared in a very controlled manner, and images taken with very low dose, very low electron dose. So when you do this, you can get images like this. This is the famous system of Doxil of Chezi Barnold, who is here. And you can see that nowadays, with this combined technology, we are able in each liposome to show the bilayer of the lipid membrane. Inside, we can see the Doxil crystal, and even more, you can see that in some places the Doxil crystal is twisted. So this is just to demonstrate what you can do with that. All right, so finally, let's go to, with all this nice technique, let's go and see what we can get. So these are extracellular vesicles, and this was our first paper on the project some 5 years ago. And what is very interesting here is that, as was said in the first talk, that the extracellular vesicles are very, very different from each other. So you can see we have granulated ones, we have smooth ones, we have some that they have protrusions on their membranes, and this is something that is quite typical for what we see in extracellular vesicles. Of course, in these images, you can also appreciate, I think, the preservation of the structures in the electron microscope specimen. This is something which is newer. The other ones were taken after inducing blebbing by starvation. Here you have extracellular vesicles that were taken after LPS stimulation. This is work of Idan Biran, my student who is here. And I do urge you to go and visit poster number 7, where we can discuss many more details. Again, note the preservation, the different structures. In this case, we really see there is something sticking here, maybe some immuno-related molecules sticking from the membrane. So these are the extracellular vesicles. Now the question is, how are they formed? And this is something that we cannot address by transmission electron microscopy because we are limited by the thickness of the specimen. So we cannot fit an entire cell in the specimen. To do this, we need the scanning electron microscope, and the scanning electron microscope allows us to look at surfaces. We can take a suspension of cells, we can vitrify it, cool it very fast, fracture it, and look at the surface of the specimen. Again, we have invested quite a bit of work into the specimen preparation, which I will not describe here, but here you have just a schematic to remind you that there is something behind it. And this rather complicated slide, which is taken from a 2012 paper with my former student Leon Isman, shows you that we have a mechanism or a system that allows us to prepare cryo-SEM specimens at controlled conditions, which is really very, very important. So basically, you prepare the specimen, you transfer it to the scanning electron microscope, and you keep it in the electron microscope at very low temperature, and you look at that fracture surface. In addition, we don't have to use coating. If you apply the right acceleration voltage on the order of 1 kilovolt only, which you can do only with the high-resolution field emission gun scanning electron microscopes, you don't have to coat your specimen, which means that you also gain through the resolution of the system. All right, so what can we see here? So here you have a cancerous cell, the monocyte, fractured in two different ways. I'm not going to go into the details, but in this case, the fracture went through the cell, but the fracture did not go through the nucleus. So this is really the exposed nucleus, and here you can even see the membrane of the nucleus. In this case, the fracture went directly through the cell and through the nucleus. There are two different kinds of preparing the specimen. I will not go into the details. But here is what I really wanted to share with you. What we have here is, again, a monocyte after 4 hours of LPS incubation. And this is the time where you can capture the blebbing of the extracellular vesicles. So in this case, for instance, you see the fracture that went directly through the entire cell. And look at this here. These are the blebs, the extracellular vesicles in the process of forming. In fact, here is one that is almost completely formed, and on the outside, you can see some that already have left the membrane. So we are able to capture it. In this case, the fracture actually went through some of these extracellular vesicles in such a way that you see them as in their entirety, that is, the fracture surface went above them and not through them. This one, I think, is my favorite, and I should mention that this was taken by my former student, Dr. Naama Koifman, and this is published now. And this is just a magnification of the previous one. And look here at the activity at the interface of the membrane and the outside suspension, and you can see very well various stages in the blebbing of the extracellular vesicles. Just as a bonus, you see here that the fracture went over the nucleus, and you can see very well here the nuclear pores. So really, cryo-SEM can show you things that cryo-TEM cannot, and this is a technique that is much less used and should be used much more. So I have another half a minute before questions, and this is just the current status of the work. We are trying to use in the liquid phase immunogold labeling, which is very different from the classical immunogold labeling. In classical immunogold labeling, you dry your specimen, and then you do your immunogold labeling, attaching the nanoparticles of gold in one way or another. In this work, we are trying to do it, again, in the sake of specimen preservation. We try to do it in the liquid phase. And in this case, you see here an extracellular vesicle, which has been very nicely labeled. And more information about this, go to poster 7, talk to Idan. So in these few minutes, I hope that I was able to show you what one can do with the very careful use of the very current technology of both cryo-TEM and cryo-SEM. And at this point, I will stop and wait for your questions. Thank you very much.
Ishi, thank you for the great talk. I just want to ask. Please use the microphone. Yeah, so people were mentioning earlier also the difference between one EV and another. And what percent do you seem empty on the inside, and what percent seem to have different material?
Okay, we haven't really done that work completely, but we have tried, and actually the labeling is in an attempt to distinguish between extracellular vesicles and MPs, okay? And from preliminary data that I didn't want to show yet, and some of it is on the poster, is that actually the distinction by size only is not a very good parameter. We believe that if we are successful in the labeling, we will be able to tell much better which is which, what is the origin of each particle that we see in our microscopy.
I think that that's intriguing because, for example, I think one of the few methods to isolate pure exosomes is by differential ultracentrifugation. Have you looked at different?
Not yet,
okay.
Not yet. I mean, this is work in progress. Good. Otherwise, I wouldn't have been here.
Yeah.
It's a wonderful work. I have one question. From biological view, you know, I saw in your images you have after the vesicles wobbling, you know, you have a lot of holes on the cells, which you do not expect from biological view, because then, you know, you can expect that the water will go into the cell, they just explode. So can you comment on that?
These are not holes. These are not holes. What you saw were not holes. I mean, we looked at a fracture. And basically, well, I think I can, oh, I cannot go anymore back. Basically, what we see is our little blebs that are still connected to the inside. And then the neck closes. So this is really like any other process where vesicles are emitted from the are blebbed from the...
It's on there again.
Oh, it's here. Okay, very good. Thank you. It's the next one. Okay, so basically there are really no holes here. You see, once they are about to leave, the neck actually closes. So there's really no. I don't think there is a hole, as much as I can tell.
Okay.
Okay.
And the other question is compared to the previous talk, and you know, people start using engineering way to produce exosomes or exosome mimics. And can you comment, you know, whether you checked the morphology, for instance, compared to the more naturally produced exosomes and more engineerily produced exosomes?
Again, this is something that definitely can be done. And if I may emphasize one point, in order to tell those small or not so small difference, you have to use a specimen preservation methodology that really keeps the original. And when you use staining and drying, most of the differences will definitely be lost.
Please.
Thanks very much. This picture looks absolutely fantastic. I'm here. The image looks absolutely fantastic, right? So just really very powerful and a lot of information. But my question is, to what extent can you use it to get reliable, say, comparable quantitative data, or this is more or less at random, it's only a nice picture?
Okay, well, what you are saying is basically criticism that's always thrown at electron microscopy.
No, it's appreciation, not criticism, but I would like to get more.
Okay, so let me just complete the sentence. This is a very valid argument to criticize electron microscopy, and in some cases, if it's only a pretty picture, that is not enough. However, when it's a pretty picture that actually describes correctly what you have in your specimen, that's a different issue. And then, and we are still not there, you can start quantifying it by image analysis methodologies. So this definitely can be done. We are not there yet, but in principle, there shouldn't be a problem doing it.
Thanks very much.
Sure.
Final question for Joy.
Yes, thank you so much. I thought it was very fascinating that some of them had these tiny extensions surrounding them. So it's related to the previous question. Can you quantify how many of them had this, and is it in response to stress or specific cell lines?
Well, this is serious now, not a joke. I'm really happy about this enthusiasm that I hear and the need for this information. We are not there yet, but definitely this is something that once we are beyond just methodology development, with, of course, examples, we will be able to concentrate on specific systems and actually do the quantification. with modern computers and image analysis software, this is not too difficult to do.
But roughly, now that you've done a few images, how often do you see them, the vesicles with the extensions?
About 50%, roughly.
50%?
Yeah, roughly, yeah.
Great. Thanks a lot.
Thank you.
Speaker again.